Hi, my name's James Philbin. I'm the Senior Director of Perception and Prediction here at Zoox.
Hi, my name is Sarah Tariq. I'm the Director of Computer Vision.
And today, Sarah and I are going to take you on an autonomous drive through San Francisco from a couple of months ago.
I want to mention that this drive is completely autonomous with 0 disengagements. And this is the first in a series of videos that we are going to be sharing, showcasing our autonomous driving capabilities.
Okay, so here we are at the start of our run, and here you can see our vehicle actually just turned from gray to white. So that's a sign that we're now in full autonomous mode. And here's the first interesting scene in the video. So we actually did a right turn on red there, and actually that requires really good perception to the left of us so we can understand that we're able to execute that maneuver safely. We're constantly striving to improve our perception stack, but today you may occasionally see small errors. For example, detecting a sign as a pedestrian. We call this a false positive.
So there's not often a lot of space in the city, and throughout this video you see examples where we have to nudge around vehicles like this one over here, or even people as they're coming out of their vehicles. You'll notice that entities have different colors, and those correspond to some of the different classes that we're detecting. For example, on the panel in the bottom, cars are in blue, pedestrians are in pink, you'll see bicyclists in purple. Internally, we are actually calculating many more fine-grained classifications, which we're not visualizing here so as not to clutter the scene. But these classes include, for example, different types of vehicles like buses, trams, construction vehicles, different types of construction obstacles like cones and lane dividers, animals, several fine-grained pedestrian attributes like whether pedestrians are standing or walking, which way they're facing, whether they're looking at their phones or even riding an e-scooter.
Yeah, so it's important to know that for autonomous driving, there is no one sensor modality that fully solves for the entire problem. And so a key feature of our stack is really good multimodal sensor fusion through cameras, LiDAR, and radar. And actually, in these videos, you can see B, L, and R means that that respective modality has contributed to that detection. So perceiving and nudging around obstacles like this bus that was parked partially in our lane then requires actually crossing into the next lane, which requires really good perception and prediction of objects behind us. And to do that, obviously, we have a 360-degree field of view sensor architecture. And a planner that's sophisticated enough so it's not just on rails, it actually can correctly maneuver and plan through the city in a fully geometric sense.
There is a very high density of people and objects in the city, and we have to perceive, track, predict, and plan for all of them in a real-time budget. In some dense parts of the city, we may need to detect and track 100 people and vehicles simultaneously.
So here you can see we've actually entered a tunnel, and this is typically a real failure case for most localization systems, as GPS completely drops out in this case. So this is a really good test of the robustness of our localization system to continue to localize our vehicle in the city from only odometry and our sensors.
So you'll notice that there's construction vehicles to the side over here. They're not blocking us, but in general, there's usually a high chance that we are going to encounter construction in the city. And it can range from just some cones that are blocking our path to having people directing traffic and having cones that make new lanes for us to follow. And these are all situations that we need to be able to handle autonomously.
So here we have to do, we're going to do another right turn on red. And up ahead, actually, you can see a pedestrian there crossing out of a crosswalk.
So we need to know when people are double parked in the lane ahead of us so that we can go around them. But we also have to be really good at detecting situations when traffic is just backed up so that we don't falsely call these vehicles as DPVs and try to go around them, which would not be cool.
And actually, predicting DPVs is a non-trivial problem. So some of the cues we use for that feature is things like vehicle lights, the position in the road, and the behavior of other traffic around that vehicle. So here's actually another interesting scenario where this vehicle is reversing into a spot there. And we need to understand that so that we can stop far enough back that we're not going to block that vehicle and cut them off. And to do that, we actually, again, use a lot of different cues, things like the reverse vehicle lights, and also, again, their positioning within the road, and also the positioning of vehicles in the parking lane. So yeah, we put all those things together inside a machine learned model, and that actually produces this signal that that person is parking.
So there's many such four-way intersections in the city, and it's actually quite complex dealing with them properly because many people will take your right of way.
So coming up here, we see one of the geographic features that San Francisco is most well known for, which is hills. And hills typically present a big challenge for sensor architectures. We've actually designed our sensors to be fully robust to actually large inclines and declines. And that makes us be able to drive very safely in cities such as San Francisco. So here you can see one of the features of our planner, which is again related to this not driving on rails. And there we were able to weave between those vehicles in quite a natural way.
So we're coming up now on Lombard Street, which is really a tourist hotspot for San Francisco. There's always a lot of pedestrians on the top and the bottom of this road. And the difficulty of Lombard is not only the controls to be able to weave through this road, but really understanding and reacting to all of the pedestrians that we encounter here.
Yeah, and this is actually a very good test for our control system. So the positioning of our vehicle here on the road and our controls in the vehicle need to be extremely accurate in order to do this zigzag maneuver accurately and safely.
And note that there's vehicles that are parked all alongside this road, and it really sometimes requires us to squeeze past them, like over here.
And here we're coming up to the bottom of Lombard. So we often see many pedestrians gathered here taking photos, and it's a real sort of tourist hotspot. One of the challenges with dealing with pedestrians like this is actually understanding their intents. And so here, our vehicle is creeping into the intersection, and we actually have to wait for these pedestrians to, leave the road surface. And there's a lot of complexity here in making sure that we are safe around these pedestrians, but also assertive so that we don't get stuck and cause a traffic hazard. And so here's a vehicle completely stopped and double parked in our lane. And here we have to actually detect that and seamlessly go around it rather than get stuck behind it, expecting it to be moving. So I thought I'd take a moment to mention some of the visualizations here you see in the bottom pane. So that gray surface here, it represents the allowable planner area that it can plan within. And then the green corridor represents the path of our vehicle into the future. So the red curtain there represents our planner stop gate. In this case, you're seeing that because of the red traffic light in that junction.
Road geometry in the city is often quite complex and requires our system to be quite general to react appropriately, for example at this 5-way intersection. And speaking of complex interactions, we just changed lanes there in anticipation that we need to turn left further up the road. In case the left lane would have been occupied, we would have deferred changing lanes to later. This behavior falls naturally out of Action Search, a feature which aims to make forward progress in a smooth and consistent way while never violating safety limits.
So often at complex intersections, we actually need to make unprotected left turns. That means we need to see vehicles driving towards us from a pretty far distance, anticipate a break in traffic, monitor traffic signals, and then potentially execute our turn within this gap. And putting that all together can be quite complex. For instance, here we have to execute that maneuver at this 6-way intersection.
The city is usually a really busy place, and this seems to be one of those roads where every delivery truck is looking to unload its goods. And if you can't figure out that they are parked, you will be stuck forever waiting for them to move.
So frequently at 4-way stops, one may technically arrive at the stop before other vehicles, but you have to anticipate that and react to the fact that sometimes others will take our right of way, or sometimes others will be unable to take their right of way due to other entities. For instance, here at this intersection, we technically arrived here before that vehicle to the left, but we had to yield.
This street really shows off how good our perception and controls are. Note how closely these vehicles are parked on either side of the road. We need to be really accurate in determining their extents, and then we need to be really good about being able to follow a trajectory that we plan in order to weave confidently through them.
So up ahead, you can see our perception system detecting and tracking a large number of pedestrians to the right. These are actually people in line for Mums, a famous San Francisco breakfast spot. I mentioned perception errors earlier in the video, so I wanted to share some more information on that topic. We bias our perception output to be conservative, in the sense that, if something looks person-like, we may occasionally misclassify it as a false positive person, even if it's actually something else. While proper classification is important for prediction purposes, the most important thing is to never miss an object that actually exists.
Here we have another double-parked vehicle that we detect and go around. And then up ahead, we detect the open door of the red car to our left and the person next to it. Open doors are one of the key hazards in the city and one that autonomous vehicles have to be able to handle safely.
So here's a good example of the range of our perception system. The vehicle up ahead there, a few blocks actually, is over 130 meters away.
Earlier, I talked about some of the colors that you're seeing in the panel at the bottom, the blues for cars, but there's also many gray objects here, and those are the static things that we perceive in the environment, poles, walls, things that are not going to be moving, but are still important to drive around.
So another hill here in San Francisco, here we're coming up to an occluded crest. So we actually need to understand that we can't see directly over this hill, and the planner will take that into account appropriately.
So speaking about the planner, the way that we're deciding where we're going at any given time is multi-layered. So at the very highest level, you can think about our planning sort of as the same as Google Maps might be doing. So you're trying to go from point A to point B, you decide what is the route you take. But then planning is much more complex because as you're driving, you're choosing at any moment what is the lane you're going to be using, what is the road you're going to be using, if a lane is blocked, and all of that is being planned in real time. Pedestrians can cross the road at any point, and in a crowded city, this is really challenging since they step out from behind cars that occlude them, and they can also stand really close to these cars and to our lane, such as here.
So here's something interesting you might miss if you blink. It's another Zoox car passing us.
Over here, we're on the leftmost lane of a multi-lane road, and after this intersection, we will need to start making several lane changes in order to finally end up in the rightmost lane where we need to make a right turn. While making these lane changes, we need to be aware of the traffic in front of and behind us and safely squeeze into the right gap. And so we've already made a couple of lane changes, and here now we make our final lane change, so we're positioned to make our right turn.
And here we're in the heart of downtown. This is typically where we see the highest density of agents in the city.
So notice these lane markings on the road. If you're not familiar with San Francisco, these might not be obvious, but there's many trams that are going through San Francisco. We might not see them in this video, but many times there will be trams with people hanging onto them, and you need to be able to understand not only that this is a vehicle, but that there's something special about this vehicle and it obeys specific rules, and we have to obey specific rules when interacting with this vehicle. So for example, when trams are in the middle of an intersection, you're not supposed to enter that intersection.
And here actually there's a flashing red light, and this means it's a four-way stop, which some people, as you can see, just ignore. After that, we see that people decide to cross the crosswalk after we're already in the junction, but we still need to stop safely behind the crosswalk for them.
So here we detect the left arrow traffic light and understand that we have right of way, and we take a protected left. Robustly and safely detecting and classifying traffic lights is a key perception task, and one that we do with a very high level of accuracy.
So here's another good example of how tight driving in the city can be. We don't have much space in our lane, and that van next to us is right on the edge of its boundary. Being able to drive in this environment safely requires a lot of precision in our stack, all the way from sensor calibration, through the perception algorithms, and all the way down to our low-level controls on the vehicle.
It's important to be able to detect and safely handle unexpected situations, like this bicyclist that is coming the wrong way and squeezing through traffic. We detected that oncoming bicyclist and determined that since there was not enough space to go into the right lane to avoid him, that is the safest thing to stop, let the bicyclist pass us before then continuing.
Also, people like that vehicle in front of us can cut out of parking spots and into our lane at any time. And we have to be prepared to let them in, but at the same time, you can't be spooked by every parked vehicle that you see. So we use a sophisticated set of low-level signals, such as vehicle lights, and high-level prediction models to determine when a parked vehicle might be trying to cut into our lane.
Handling yellow lights properly involves us having to predict how long they will remain yellow for, and also using surrounding traffic flow to estimate if it is acceptable to proceed through a junction or not.
And here we see the opposite situation to the one we saw earlier, where that car was trying to park. And so we needed to detect that intention and then pass around it rather than get stuck behind and try to follow it.
Note that our system can correctly track pedestrians even if they are pushing, pulling, or carrying other objects, such as this mother with a stroller to the left of us.
Here we have another right on red, although this one's a bit simpler from the previous ones as there's no cross traffic to worry about.
So here we are stopped near Market Street. It's another really famous spot in San Francisco, and there's a lot of pedestrians and cars that we'll see in this scene, and we're able to detect, track, predict all of them in real time. Understanding and obeying traffic signals is vitally important for safety. In our vehicle, we have a very robust system that is built on redundancy. We have several different cameras that are able to observe and classify all the traffic signals at an intersection, and then reason jointly about the state of the intersection. Our cameras have different fields of view, so we're able to detect and classify the traffic lights quite early. So for example, more than a block away for this yellow light, and that enables us to smoothly slow down for the upcoming transition to a red light.
Okay, so Sarah just mentioned the cameras that we use to detect traffic lights. So I thought it'd be nice to take a moment to mention our sensor stack in more detail. Our stack consists of 3 modalities, so cameras, radars, and LiDARs, which all work together to give us the best possible perception. We have actually 18 cameras, 10 radars, and 8 LiDARs, and we use those overlapping field of views to give us a system which has a lot of redundancy and safety built into it from the bottom up. This many sensors would be pretty expensive if you had to pay for them on your own car, but we're able to amortize their cost over our vehicle's entire service life, which makes them quite affordable per ride and totally worth it because of the added safety they provide.
Our perception system is good at detecting objects even when they are heavily occluded. Here you can see that we are correctly detecting a line of 4 separate vehicles across the junction facing towards us.
Here's another example of an unprotected left turn. We have a green light, but we have to yield here to oncoming traffic and find a gap in which we can safely go. So here's something funny. We actually encountered and go around 3 double parked vehicles, one by one. If you're paying close attention, you would notice these are actually Zoox vehicles. It's not unusual to see Zoox vehicles out and about in San Francisco, especially in the difficult areas that we're showing in this video. although having 3 in a row is not something I've seen very often.
So we've been talking about the different parts of our autonomous stack, and I thought I'd take a moment to just walk you through it. Our stack starts by taking all the input that we have about the world, all of our sensor data, like radar, LiDAR, camera. It goes through perception, which is responsible for understanding what all of this sensor data means. And so from images, we are able to tell where are the placement of all of the objects in the scene and what are their classifications. Same with the LiDAR and radar data. Once you've got this idea of what are all of the dynamic and static things in the world, what are their velocities, what are their attributes, the next part you want to do is try to understand for all of these dynamic things, how are they going to move in the future? And so for a person, what is his path? For a vehicle, what is its next intention? Is it turning? Is it going straight? All of this prediction then feeds into Planner. Because if you think about it, when you're driving your car, in addition to thinking about what's happening at the present moment, you're thinking about what is going to happen 2 seconds or 5 seconds down the line. And so Planner takes into account all of this perception and prediction data and then makes a plan about what our vehicle should do, considering what we expect other vehicles to be doing. And this back and forth between what should we do and how are the other people behaving is actually quite complex and quite nuanced. All of that information, our plan of what we're going to be doing in the short term, where are we going to be driving, what lane are we going to be using, what is our speed, what is our steering angle, is then fed into low-level controls which are actually responsible for talking to the vehicle's braking and steering interface. And that's how we command the vehicle to do what we want it to do. This is a really busy intersection, and one thing I'd like to point out is that amount of traffic lights in this scene, each pertinent to different roads and different lanes. Without having a map, given just an image, it can be very hard to figure out which traffic light is the one you have to pay attention to. In our case, since we drive in regions where we have already mapped, we know exactly which of these traffic lights applies to us.
During these multi-lane parts of the city, traffic often doesn't stay cleanly in their lanes, and they'll often change lanes suddenly. Having a planner that can reason geometrically in these cases and low latency prediction is crucial for handling these types of situations well. This bus up ahead is almost entirely blocking our lane, but our planner is able to understand that situation, understand that the lane to the left is free, and nudge appropriately.
As I mentioned before, because we have a highly detailed map of where we drive, we know which traffic lights are pertinent to us. In this intersection, we are detecting and classifying the traffic lights that are facing us, but we are also detecting and trying to classify the traffic lights that are pointing towards other roads, like the ones to our left.
Here's another reason why having maps is useful. Here we're trying to make a left turn, but there's actually a sign above the traffic light indicating that left turns are prohibited, along with a text about why. Since we already have this intersection mapped, we know exactly what these restrictions are. We don't need to waste compute cycles trying to understand that information in real time. Also, since this is another unprotected left turn, we need to yield again to this oncoming traffic and find the gap where we can go.
Here's an interesting situation. We have to stop at this intersection, but the traffic to our right and left does not. In addition, our view of that traffic is blocked due to occlusions, especially to our right. In these cases, our planner is using the perception system to understand not only the traffic that we can see, but the areas that we know are occluded, which might have unseen vehicles in them. The planner then uses this information to creep into the intersection until perception tells it that we can now observe any traffic. At this point, we verify that there are no oncoming vehicles before we proceed safely through the intersection.
There are lots of subtle rules that humans use when driving that we also have to make sure our autonomous vehicle follows. Here's one. When we are making a right turn in a road with a bike lane, we need to properly merge into that bike lane into the mixing zone, which we do here. This is important so that bicyclists in this lane understand our intention to turn right and so that we can return safely.
Okay, and here we are back at base. Note that the color of the icon of our vehicle changes from white to gray, indicating that this is the end of our mission and we are now handing control back to the safety driver.